Welcome to this video on multi-attribute utility. In this presentation, we're going to go through an example on multi-attribute utility. Let's examine a problem involving uncertainty and multiple attributes. In this example, let's say you're looking for a new job and you've narrowed down your options. There are three possible jobs. If you're making a career change, or let's say you're contemplating possibly shifting careers, or moving within your company, etc. There are a lot of factors you have to think about. These are all different attributes. Oftentimes it's difficult to express your preferences among these jobs across these preferences. So for example, one of the jobs might have a very different salary, significantly higher, or one of the jobs may have in a location that you really prefer. Another job might give you a better growing opportunity, etc. There could be a long list of different factors that are involved when you're trying to make this decision, and how you prioritize, or the way you rank these preferences may be different. Um, this is a type of multi-attribute problem. Okay, so let's give an example here. So let's compare the various combinations. Let's say you have a job that offers $70,000 a year, it's in New York, and it's got very good promotion opportunity, versus another job with a slightly higher salary of 80,000. It's located in San Francisco instead, but it's got a lower promotion opportunity. Um, how can we compare these two to make an apples-to-apples comparison? What's one way can we approach this so that we can make a more rational decision? Okay. An alternative approach to if you're trying to make this decision on the surface, I think it's pretty difficult. I would find this decision to be very difficult. So alternative approach is to consider each factor separately, then combine. Okay. So for any job, the total utility of that job is a combination of the utility of that salary value, the utility of that location, and the utility for that opportunity for promotion. This will be one way to kind of see what the total utility is for that specific job offer. This could be one way to do it. So this approach, simply adding up the utility for each one of these attributes and combining them, might work. Yeah, but there's some drawbacks of this approach. The caveat here is that this type of additive utility function assumes that when you change one of these attributes, it doesn't depend on the values of the other attributes. So for example, if the utility of the salary goes up, it has no impact on the utility of some of these other factors. So there's basically no coupling or no dependency among these attributes. This may not be the case, right? So this is a more simple, simplistic approach to multiple attribute utility. So another way of going about this then is maybe a more complex version of this is maybe you don't do an additive case. You look for a non-additive case. So the case that we're going to look at is a multilinear utility function, which captures a limited form of this interaction between the attributes. So again, there's many different ways to do this that are much more complex. But for simplicity in our discussion here, we're going to just assume a very limited multilinear form that tries to account for this interaction between attributes. Okay, so the general form here is that if we have two attributes, x1 and x2, okay, the utility of those combined is described with the following equation. So each utility has some factor k, ki, so k1 for factor 1 or attribute 1, k2 for attribute 2, and really it's the last term here. This last term here, this captures the interaction between attribute 1 and attribute 2. So the claim here is that change in attribute 1 has an impact on attribute 2. Okay. Each utility function ui is scaled from 0 to 1 when we're calculating this multilinear utility function. Let's demonstrate this multilinear utility function with an example. Let's say your company is developing a new bicycle braking system, and then two alternatives have been proposed. One will mainly use plastic components, while the other uses mainly metal components. The ideal product will be lightweight and durable, but there's uncertainty about the characteristics of the final product. This applies to both alternatives presented here. Step one in this case, so here you have a choice to make, right? You got to decide whether you're going to use plastic components primarily or you're going to use metal components primarily. But when you make this decision, there's a trade-off between weight and durability, right? So those are like the attributes you have to think about when trying to make this decision, right? So we start by deriving a single attribute utility function first. We can use a set of lotteries to list the utility values, same thing we did in the previous modules, and to come up with some kind of utility function for each one of these. So in this case, let's assume that for our company, being lightweight, let's say assume 120 grams is the best, and we're going to assume the utility is 1 there. And the worst case scenario is a weight of 290, that's the heaviest, the utility is 0. The durability is captured by the guaranteed lifetime in years. So we want higher durability, right? So lifetime of 3 years, we're going to give it a utility of 1. And then the lifetime guarantee of 1 year, we're going to give it a utility of 0. So again, we're not gonna go into the details of how we came up with these values. Please refer to the previous modules on what are some ways to elicit these utility values from the decision maker, but we're gonna assume that it's there and this is the result. Now we continue on to step 2. We're going to combine the single attribute functions to obtain a multi-attribute utility function. So we've assess the utilities for the 2 attributes. The first attribute being the weight, and the second attribute being the durability, or in this case, the guaranteed lifetime in years. In order for us to proceed, we have to get more information from the decision maker. So further questioning the project team leader indicates that the decision maker is indifferent between the following 2. Option A, which is a product which was certain to weigh 130 grams, but which had a guaranteed lifetime of only 1 year. If you notice this option, the 130 grams is the highest utility for attribute 1, which is the weight. And it's the worst in terms of attribute 2, the guaranteed lifetime is 1 year. So this is the best in terms of the first attribute. In option 2, a lottery that is offered a 70% probability that a product would have weighed 130 grams and a guaranteed lifetime of 3 years, and a 30% probability of a product with a weight of 290 grams and a guaranteed lifetime of 1 year. All right, so you're gonna have to see where this is going. Based on what's offered here, these 2 options are really aimed at getting the value of K1, the coefficient for the first attribute. Okay? So if we draw out the probability trees here, option A looks like this, right? There's 100% probability you're going to get the best of attribute 1 and the worst of attribute 2. Okay? The decision maker is indifferent between this option and option B, which gives you which is 70% probability of the best in terms of option attribute 1, the weight, and also the best in the durability or the guaranteed lifetime years, which is 3 years. So if you look at this picture, this is basically saying the decision maker is indifferent from the swing from a guaranteed lowest weight, which is the best weight possible, to this case of there's a 70% swing basically from the best to the second option, which is the best of both options, and the worst of the first attribute, right? So if you look at this bottom tree here, you're going from the best to the best to the worst of the worst. So basically, this is K1. The 70% here, this is the value of K1. Okay, and then the 0.3 is 1 minus K1. And we can kind of tell by looking at this equation where this comes from. We look at the multilinear attribute equation. If you plug in the values here, K1 times the utility value for utility 1, which is 1 in this case, the best weight, plus K2 times the worst of the durability, which is 1 year, which is 0 for utility. Okay, so we're looking at this value over here, and 130 grams, 1 utility there. And then this part is the coefficient in terms of this combined term, 1 times 0 obviously is 0. This ends up being K1. Okay, so using one of our axioms, then we know that since these two lotteries are the same, um, the coefficient K1 must equal 0.7. We can now proceed to find the weight for K2 next. Um, so further question. We're going to further question the the team leader. Again, we have um, the utilities, individual single utility function values already. Now we're offered the second set of options. Option C, a product which was starting to weigh 290 grams, but which had a guaranteed lifetime of 3 years. So this option is basically the best in terms of attribute 2 and the worst of attribute 1. So again, I'll call this attribute 1. Attribute 1 is the weight. Attribute 2 is the durability of the life in years. So option C is the worst of attribute 1 and best of attribute 2. Option D then is a gamble which offered a 90% probability of a product with a weight of 130 grams, which is now the best in terms of attribute 1, and a guaranteed life of 3 years, the best of attribute 2, and a 10% probability with a product with a weight of 209 grams, worst of attribute 1, and a guaranteed lifetime of 1 year, worst of attribute 2. So it's very similar to the last set of probability trees. Okay, so here's option C, and then this is option D. Okay, so based on this, we know that the decision maker, their assessment of K2 here is 0.9. Okay, so this must be K2. Okay, because they're basically willing to trade off the best guaranteed life year with the worst. This swing is basically worth 0.9. You notice that K2 value is bigger than K1. So at least for this decision maker, they value this higher than the first attribute. Okay. Again, we could look at this equation. The attribute for the worst in attribute 1 and the best of attribute 2, you just again use that equation again, you plug it in, you end up with K2. This means that for this set of conditions, the K2 value must equal 0.9, using again the axioms that we learned previously. Let's summarize, let's put the results together so that we can procedure. So based on the set of lotteries that we've offered the decision maker, we've deduced that the K1 value equals to 0.7. So again, this is the weight for attribute 1, the weight of the bike, and the weight for attribute 2, K2, is equal to 0.9, which is the weight on the durability, or in this case, the lifetime of the bicycle. So we're ready now to draw the decision tree here. Okay, so the first event, so some additional information before we draw the tree here. The plastic design, there's a 60% chance that this design will yield a 130 gram bike with a 1 year guaranteed lifetime, 40% chance that a 2 year guaranteed life and 180 grams. Metal design, 70% chance of 2 year guaranteed life, 250 grams, and a 30% chance of 3 year guaranteed life, 290 grams. So we're going to keep it simple here. We're going to assume that these are the 4 outcomes. Okay, so our decision tree then would start with the decision, right? The first event is based on what we know right now. We got to decide: are we going to go for this plastic design development, or are we going to go to the metal design development? We don't know exactly how it's going to turn out. We have some estimate now how it'll turn out. Okay, so the next event then, based on what you decide, is a chance note. Okay, if we go with the plastic design option, there's a 60% chance that it'll yield a 130 gram and 1 year guaranteed lifetime product. There's a 60% chance. And then the other option, the other possibility is a 180 gram weight bicycle that's got a rated 2 years of guaranteed life. That's a 40% probability. Okay, and then if you opted for a metal design, the two potential outcomes are a 250 gram 2 year design, 70% chance, and a 290 gram 3 years design, or 30% probability. Okay, so based on this tree right now, we actually know what the multiple attribute utility values are for some of these. So if you look at the top branch there, okay, this is the best of attribute 1 and the worst of attribute 2. So this must be the K1 value, right? Okay. So we know if you look at the multiple attribute utility, this value is 0.7. Okay, that's K1. If you look further down, the bottom branch here, 290 grams 3 years. This is the worst of attribute 1 and the best of attribute 2, the durability or the lifetime, 3 years. So this must be K2, right? So this is 0.9. Okay, so based on what we figured out previously, we have these values on a tree. Now we're going to proceed now and to fill out the rest of this tree. So we're going to now continue and figure out the multiple attribute utility values for the two other outcomes that we see on the tree. Okay, so we'll start with the plastic design that yields the 180 grams in 2 years product. So this is what we know so far based on what we had before. If you look at this chart, we created this chart based on the single utility function we had previously, right? So based on this, we can actually figure out the missing values here. Okay, so I'm going to label these as A and B. So the first part here, we're gonna figure out. Let me mark it over here. We're gonna figure out this value first. Okay, so what's the multiple attribute utility value? We'll call this A. Okay, so we're gonna figure out A first. Okay, so let's start figuring out A. Okay, so we're gonna use this equation to figure this out. So we know the multi-attribute utility function looks like this. Okay, we already know what K1 is. Okay, we know what this value is. We know what K2 value is. Okay, so again, the rule for this is that the weights have to equal to 1. If you add up all the weights, it has to equal to 1. So we know that the weight on the third term is going to be 1 minus K1 minus K2. Right? So for this situation, X1, again, X1 is the weight, is 180 grams. X2 is the guaranteed lifetime, which is 2 years, right? So we're really finding the utility of 180 comma 2, right? So we plug that in. We know what the values are. So the rest, you just look up the table, right? So U1 180, we look at this value, we're looking at 0.9. U2 2 years, we're looking at this value over here, okay? This value, U1 180, again, it's 0.9. U2 2, 0.6. We just plug those values directly in there, okay? So we plug those in, and we're going to get the result 0.846. Okay, so that means this node here is going to be 0.846. Okay, so now the next step then is we're going to have to figure out what this value is, which is labeled as B right now, and that's what we'll do next. Okay, so we're going to continue and finish out filling out the multi-attribute utility values on our tree here. So the missing value is at this rightmost one here, 250 grams, 2 years. So 250 grams, based on our table here, is we're looking at this row here, okay? And so it's all the values actually we need are in this row right here, right? Okay, so we're going to take that piece of information and to solve. So again, same as we did before, we're going to use our utility function. This is the utility function. We already know what K1 is. We already know what K2 is. So we can evaluate this part, and we know what this equals to. Okay, X1 here is equal to 250 grams. So we know the utility value for that is 0.6. X2 is 2 years, and we know the utility value for that is 0.6. Okay, so we can just plug that in now. Okay, we just plug those values in. So again, this should be 0.6 over here. Okay, and then this one should be another 0.6. Okay, coincidentally, they're just both 0.6, right? Okay, 0.6, 0.6, right? So you plug those values in, okay, and then the result here is going to be 0.744. Okay, so for that value on the right-hand side of metal design, 250 grams in 2 years, it's going to be 0.744. Okay, so we have the multi-attribute utility values now in our tree, and we're now ready to solve this tree in its entirety, and then to give a recommended decision for the initial decision node. So we're now ready to proceed and then roll back here from right to left, and to figure out the expected values of each one of these nodes. So let's start with node 1. So I've labeled as node 1. That's the top node there after from plastic design, right after plastic design. So the decision node there, I'm sorry, the chance node there, to get the expected value there, again, same as we've been doing before, we're going to take the outcomes times the probability. So it's simply going to be 0.7 times 0.6 plus 0.846 times 0.4, same as we've been doing before, right? So we're going to make that calculation, okay? It ends up being 0.7584, okay? So that's the value at this node, okay? Now we're going to move on to node 2. Node 2 is down over here, okay? Node 2 is over here, okay? So to get that value, again, same as before, 0.7 times 0.744 plus 0.3 times 0.9, okay? So you plug that, you calculate the expected value there. It's going to be 0.7908, okay? So just based on multi-attribute utility values here, the expected utility value, okay, the best decision here is to go with the metal design, right? Because it's 0.7908 is bigger than 0.7584. So we're going to draw a little arrow there, indicating that the better decision is to go with the metal design. The expected utility at our initial node then is 0.7908. Okay. So note that if based on this analysis, the multi-attribute utilities for both of these options, the difference isn't very large, right? So this is, I mean, I'll highlight this piece of information here is, decision trees. I've said this multiple times. I think it's, you don't have to follow this literally, right? But the fact that you put things down in a decision tree and you can kind of map out the different chains of events, that in itself is extremely valuable. And here, where the expected utility values are very close to one another, this is where you would have to do some kind of sensitive analysis, right? So based on the sensitive analysis, you'll see how robust your decision is. Okay, so I think that's probably one of the other really, really important and also valuable part about a decision tree is that it tells you how robust your decision is. What if the probability, for example, on this right-hand side here, what if these probabilities are way off? They're just not, maybe it's 0.9 and 0.1. How does that change my decision? Maybe the probabilities down here are very different, 0.8 and 0.2. How does that change my decision, right? So that will, definitely alter your expected values on this node, so that you'll see what the difference is between the utility values. You may also think about using a different method to elicit the utility values themselves. This was mentioned previously as well. Studies have shown the method in the process in which you elicit the utility values could have a significant effect. So maybe there's better ways to do that eliciting utilities process so that you get a better result. This is the end of the presentation. Thank you for watching.